Today I'm going to cover the fourth chapter in your Statistics 2 textbook. It's called Continuous Random Variables. Now we've come across continuous random variables before when we did the normal distribution. So what do we mean by continuous random variables? Just to recap, continuous variables are variables that don't take discrete values. So, instead of taking values in steps of say 1, so 1, 2, 3, 4, or 5, 10, 15, 20, they can take any decimal value between any two values. So it can be 1.1, 1.21, 1.31, 1.301, and so on. It can be anything in between 1 and 2, for example. All right. And random is variables that are selected by chance. So we have seen distributions of, or we've seen a particular kind of distribution of continuous random variables called the normal distribution. So the normal distribution it was a special kind of distribution of continuous random variables, and it had special features, which was it had this bell-shaped curve when you plotted it, and the curve was symmetric, and we use some of these properties of a normal distribution to calculate probabilities. This is what we used in grade 11 when we did the AS level math. Right. So the normal distribution is a subset of all the distributions that continuous random variables take. And this year we are going to cover distributions that don't look as pretty and as symmetric as a normal distribution. Okay, so we might have a distribution that looks maybe like this. So I'm going to just give you an example. So perhaps our distribution would look like this. Okay, this is, it appears to be quadratic. It's not symmetric about anything. So our continuous random variables could take any shape of distribution in this year's syllabus. Okay, so what were the features? The normal distribution had certain features that apply to all distributions of continuous random variables. Okay, so we're going to discuss those being the properties of continuous random variables. So first thing we want to talk about is this curve. This curve is the curve of the function, and we refer to it as the probability density function. Probability density function. I'm going to call it the PDF for short. Okay. Now, probability density function has certain properties which apply to all probability density functions, even the ones that are not a normal distribution function and are not symmetric or bell-shaped. Okay, so all probability density functions have certain properties. Okay, so we're going to discuss them one by one. So the first property is, if I wanted to calculate probability of x lying between x1 and x2, I would have to find this area under the curve. This area is the probability of x lying between x1 and x2. And for normal distributions, we used to standardize the curve by converting all the x values to z or z values. And then we used to use the property of symmetry of the curve to calculate phi of z, 1 minus phi of z, and so on. And that's how we found the probabilities. In case the curve is not a normal distribution, then how do we calculate the area under the curve, which again is always the probability in a probability density curve. So I'm just drawing that on this curve. So let's say we want to find this probability, which is the probability that x lies between x1 and x2. Okay. So probability of x between x1 and x2 uh, can be found using integration. So last year we realized that if you integrate a function between two limits, you end up with the area under that curve between those two limits, right? So this year, for calculating probability, because probability is the area under a probability density function, we're going to use integration to calculate that area. So we'll be integrating x1, we're going to integrate f of x between x1 and x2, and that will give us the required probability for x between x1 and x2. Okay, the second property is that the total area under the curve, which we noticed in the normal distribution as well, is equal to 1. So this entire area, I'm just shading it in yellow, the entire area was equal to a probability of 1, because total area is going to be total probability, and a total probability is 1. So same thing applies here. Total area under the curve is equal to total probability is equal to 1. If you consider our curve, which is not the normal distribution, let's say it extends from A to B, then this entire area under the curve between A and B, since this function is defined only between A and B, so this entire area is equal to the total probability, which is 1. Now in terms of integration, we can represent that as integral between A and B, which is the outer limits of the curve, of f of x dx is equal to 1. Right. The next property of a probability density function is that f of x is always greater than or equal to 0. What does that mean? It means that the graph is always above the x-axis. Why? Because you can't have a negative probability. So you will notice that every time they give you the graph of a probability density function, or if you sketch it yourself, it will always be above the x-axis, because f of x cannot be negative. These two are the defining properties of a probability density function. Define probability density function. So what do I mean by that? In your papers, you might get a question saying, this is a function, show that it could be a probability density function. So if you want to prove that something could be a probability density function, you have to prove these two. One, that the area under the curve, the total area under the curve is equal to 1. You can do that by integration. And second one is that the curve is entirely above the x-axis. F of x is always greater than or equal to 0. Now, apart from this, we also want to talk about a couple of formulae. So the first one is the mean formula. So mean or expectation, E of x, is given by the formula integral of x times f of x over the entire limits of the function. So a, between a and b. This is the formula we'll be using to calculate mean. It is given in your formula sheet, your MF19 document. Similarly, variance, the formula is again given in your MF19. Integrate between a and b, x squared fx dx, and from that you subtract the mean squared. E of x the whole squared. So these two formulae, you just need to know how to use it. You don't really have to learn it up by heart because it's available on your formula sheet. Right. Finally, we come to the last, well, not exactly, yeah, it is a property in a sense. What is a median in a probability density function? Okay, so to demonstrate that, I'm just going to redraw the graph that we just used. Okay, let's say this is f of x and this is x, and our function is defined between a and b. Okay, it's defined between a and b. Now, what is the median? The median is the value of x that divides the area into two equal areas of 0.5. So this is the area under the graph, marking it in a yellow shading. So m will be the value that divides up. We know this entire area is 1 because total probability is 1. So we have to find a value m. I'm drawing a little bit off center such that on either side you have an area or a probability of 0.5. Alright, this we can express in terms of integrals as integral between a and m being the median of f of x dx is the same as the integral between m and b of f of x dx, and both of them are equal to 0.5 because that's the definition of a median. It divides the area into two equal halves or two equal probabilities. Okay, so these are the properties and features of probability density functions, which are the distributions of continuous random variables.